Hello everyone and welcome back to the next lecture of control systems. From this presentation, we are going to start modeling of mechanical systems. In the previous lectures, we discussed the modeling of electrical networks by the transfer function approach. In the same way, we will now discuss the modeling of mechanical systems. Firstly, in this particular lecture, we will discuss the introduction of mechanical systems, the types of mechanical systems, and the parameters and the components that are involved in various mechanical systems. So, let's get started. Let us start with the definition of mechanical systems. A mechanical system is a set of physical components that convert input motion and force into a desired output motion and force. Since motion is involved in case of mechanical systems, based on the type of motion, we can divide the mechanical systems into two different categories. The first one is the translational mechanical systems, in which the motion is translational motion, that is the motion in a straight line. And the second one is the rotational mechanical systems, in which the motion is rotational. We'll be discussing about these two types of mechanical systems in great detail in this topic. So let's start with the translational mechanical systems. We know that in translational mechanical systems, the motion is translational motion. That is, the motion is in a straight line. Moreover, the equations governing such motion are Newton's laws of motion. We all have studied Newton's laws of motion in our high school physics, right? Yes, we'll be applying the same laws while dealing with these systems. So these are some important points regarding translational mechanical systems. We will now move on to the parameters of translational motion. And the first parameter is the displacement. The displacement is the change in position of an object with respect to time. And this change is represented as xt. The SI unit of displacement is meters. Moving on to the next parameter, which is the velocity. The rate of change of displacement with respect to time is the velocity, and it is represented by a letter v, and it is equal to the rate of change of displacement with respect to time. The SI unit of velocity is meter per second. Moving on to the next parameter, which is the acceleration. It is the rate of change of velocity with respect to time, and it is represented by a letter a, which is equal to rate of change of velocity with respect to time. From the definition of velocity, we know that the velocity is equal to the rate of change of displacement with respect to time. So we can say that acceleration is the double derivative of displacement with respect to time. And the SI unit of acceleration is meter per second squared. Moving on to the last parameter, which is the force. A force is a push or a pull on any object. It is represented by a letter F or f of t, and the SI unit of force is Newton or kg meter per second squared. So these are the parameters of translational motion, and we'll be using these parameters while dealing with translational mechanical systems. We will now discuss the components of translational mechanical system. Moving on to the components or the elements which are present in translational mechanical system, we can say there are three components. The first component is mass. This is the property of the system itself which stores the kinetic energy. And due to the presence of this component, a system opposes the change in its position or constant velocity. The mass of a system is represented by a letter m. Now suppose we are having a system having mass m, and if we apply a force f of t to the right hand side, then what will happen? Yes, this system will move to the right hand side. And hence we can say that the displacement of mass always takes place in the direction of force applied. This is an important point to understand. If we are applying the force f of t in the right hand side, then the displacement will also occur to the right hand side. Moreover, due to the mass m, this system will oppose the change in its position, and it is directly proportional to the acceleration caused in this system. So we can say that if we are applying a force f of t in order to move this system to the right hand side, then this force is directly proportional to the acceleration caused in this system. I hope you got this. Now if we want to remove this proportionality, we can add a constant. So we can write f of t equal to m multiplied with a. And this m is the mass of the system. And the SI unit of mass is kg. So now we are done with the first component in translational mechanical system, which is the mass. Now we will move on to the second component, which is spring. A spring is an elastic object that stores potential energy. We might have seen a spring in our daily lives, I'm sure. And we know that a spring tries to regain its original position when we try to compress or elongate by applying a force. Let us try to understand this in a better manner by the use of this diagram. This is a spring which is attached to a fixed support from one side, and on the other hand we are trying to elongate it by applying a force F of t. Then there will be a displacement x of t in the right hand side, and the size of the spring will increase. Now we know that if we try to elongate this spring, it will try to regain its original position due to the presence of potential energy stored inside the spring. So what will happen? Yes, the spring will apply a force opposite to the direction of F of t in order to regain its original position. And that force is directly proportional to the displacement caused due to this force. And hence we can say that F of t is proportional to x of t. Now, if we remove this proportionality, we can write F of t equal to k multiplied with x of t, where k is the spring constant. The spring constant is unique for a particular spring and it defines the stiffness of the spring. And the unit of spring constant is Newton per meter. In this way, we are done with the discussion on the second component, which is the spring. We will now move on to the third component, which is friction. It is defined as the force which opposes the relative motion. The friction is represented by using a damper or a dashpot. This is a damper or a dashpot which represents the friction existing between two bodies or a surface and a body. So if we apply a force F of t to the right hand side, then there will be a displacement x of t to the right hand side. But there will be an opposing force of friction which will act in the opposite direction to that of F of t. And that force is proportional to the velocity of moving object. So we can write Fv of t proportional to dx over dt, where Fv of t is the opposing force due to friction and dx over dt is the velocity of this system. We have written this force as Fv of t because it represents the force due to viscous friction. There are three types of frictions. The first one is the viscous friction, the second one is the static friction, and the third one is the Coulombic friction. Out of these three frictions, the viscous friction is the dominant one, and that's why we consider only the viscous friction. So now we know that Fv of t is the opposing force due to viscous friction and it is proportional to the velocity of the system. Now, if we want to remove this proportionality, we can add a constant and we can write Fv of t equal to b multiplied with dx over dt. In this expression, b represents the frictional constant or the coefficient of viscous friction, and the SI unit of frictional constant is Newton second per meter. We can also verify this unit of frictional constant by using the same expression. We know that Fv of t is the opposing force due to viscous friction and the unit of force is Newton. Moreover, dx over dt is the velocity of system and hence the unit of this will be meter per seconds. So if we transpose dx over dt to the right hand side in order to calculate the units of frictional constant, we will have the SI units as Newton second per meter. I hope you got this. So in this way, we are now done with the discussion of components in translational system or the elements present in translational system. We will now move on to the discussion of rotational mechanical system. Moving on to rotational mechanical system, we will first see the definition of rotational motion. The rotational motion is defined as a circular motion of a rigid body about a fixed axis. So we can say that if a rigid body is experiencing a circular motion about a fixed axis, then in that case it is a rotational motion. And we can say that the mechanical systems which experience rotational motion are called as the rotational mechanical systems. So in this way, we are done with the definition of rotational motion and the introduction to rotational mechanical system. We will now move on to the parameters of rotational motion. The first parameter is the angular displacement, and it is defined as the angle in radians through which a rigid body rotates about a fixed axis. It is represented by an angle theta. Let us understand the angular displacement in a better manner with the help of one example. Consider this rigid body which is rotating about an axis passing through its origin in anti-clockwise direction. Now consider a point P1 which is present on the positive x-axis. Since this rigid body is experiencing a rotating motion in an anti-clockwise direction, we can say that after some time this point will move to position P2 which is present in the positive y-axis. Now this change in the position of point from P1 to position P2 due to the rotation of this rigid body is called as the angular displacement, and it is measured in radians, and hence the SI unit of angular displacement is radians. So tell me, what is the angular displacement of this body if point P1 moved to point P2? Yes, the angular displacement is of 90 degrees, or we can say the angular displacement is pi by 4 radians. So I hope you understood the first parameter, which is the angular displacement. We will now move on to the second parameter, which is angular velocity. It is defined as the rate of change of angular position or angular displacement of a rigid body if it is undergoing a rotational motion. The angular velocity is represented by a letter omega, and it is equal to the rate of change of angular displacement with respect to time. The unit of angular velocity is radian per second. Now moving on to the third parameter, which is the angular acceleration. It is the rate of change of angular velocity if a rigid body is moving in a rotational motion. It is represented by a letter alpha, and it is equal to the rate of change of angular velocity with respect to time. From this equation, we know that the angular velocity omega is equal to the rate of change of angular displacement with respect to time, and hence we can say alpha, which is the angular acceleration, is equal to the double derivative of angular displacement with respect to time. The SI unit of angular acceleration is radian per second squared. Now moving on to the fourth parameter, which is the torque. In case of translational mechanical systems, we had force as the fourth parameter. Similarly, in case of rotational mechanical systems, we have torque. So it is the measure of how much a force acting on a body causes that body to rotate. In case of translational mechanical systems, we were using the force in order to move a body in a straight line. Similarly, in case of rotational mechanical systems, we are applying a force in order to rotate a body through a certain angle. And that force in case of rotational mechanical system is regarded as the torque. It is represented by a letter tau, and the SI unit of torque is Newton meter or kg meter squared per second squared. So these are the parameters which are present in rotational motion. We'll be discussing these parameters as we deal with rotational mechanical systems. We will now move on to the components or the elements present in rotational mechanical system. So moving on to the components in rotational mechanical system, there are three components, or we can say three elements present in rotational mechanical system. The first one is the moment of inertia, which is defined as the property of a rigid body by the virtue of which it opposes the change in its angular position or angular velocity. It is represented by a letter J. So the moment of inertia is a property of rigid body by the virtue of which it opposes the change in its angular position or angular velocity. Let us understand this with the help of one example. Suppose this is a rigid body and we are applying a torque tau in order to rotate this body about this axis. Suppose this body rotates about an angular displacement theta t. Then in that case, due to the presence of moment of inertia, this rigid body will oppose the change in its angular position, and that opposing force will be directly proportional to the angular acceleration of this body. So we can write tau is directly proportional to alpha, where alpha is the angular acceleration caused in this rigid body due to the application of torque tau. Now, if we want to remove this proportionality, we can remove this with a proportionality constant. So we will have tau equal to J multiplied with alpha, where J is the moment of inertia of this rigid body, and the unit of moment of inertia is kg meter squared. Now we know that alpha is the angular acceleration and it is equal to the double derivative of angular displacement. So we can write tau equal to J multiplied with d square theta t over dt squared. We have replaced alpha with double derivative of angular displacement with respect to time. Now let us try to apply Laplace transform on both the sides. So if we apply Laplace transform, we will have tau s equal to j multiplied with s squared theta s, where theta s is the Laplace transform of theta t and tau s is the Laplace transform of tau. J is a constant, hence it will remain as it is. In this way, we have the torque equation as tau s equal to j multiplied with s squared multiplied with theta s. This is an important equation. We will be using this torque equation while dealing with the rotational mechanical systems. Now moving on to the second component, which is the spring. We already know that the spring is an elastic object that stores potential energy. Let us consider a spring which is attached to a fixed support from one side, and on the other side we are trying to rotate this spring by applying a torque tau. Let us consider the angular displacement caused equal to theta t. In this case, we know that the spring will try to regain its original position by applying an opposing torque, and that opposing torque will be directly proportional to the angular displacement caused due to the application of this torque. So we can write tau is proportional to theta t. If we remove this proportionality, we will have tau equal to k multiplied with theta t, where k is the torsional spring constant and the unit of k is Newton meter per radian. Now, if we try to apply the Laplace transform on both the sides, we will have tau s equal to k multiplied with theta s. And this is the torque equation in case of a spring when we apply a torque tau in order to rotate the spring. I hope you got this. We will now move on to the third component, which is the friction. We already know that the friction opposes the relative motion between two objects. In this case, the relative motion is rotational in nature. So if we consider a damper or a dashpot which is attached to a fixed support from one side, and on the other hand we are trying to rotate this by applying a torque tau, and due to this there is an angular displacement theta t, then in that case this damper will try to oppose this rotational motion by applying an opposing torque, and that opposing torque will be directly proportional to the angular velocity. So we can write tau is proportional to d theta t over dt, where derivative of theta t over dt represents the angular velocity due to the application of this torque tau. Now if we want to remove this proportionality, we can write tau equal to b multiplied with d theta t over dt, where b is the torsional frictional constant and the SI unit of b is Newton meter second per radian. Now, if we apply Laplace transform in this equation, we will have tau s equal to b multiplied with s theta s. The Laplace transform of d theta t over dt is s theta s, and the Laplace transform of tau is tau s. And this is the torque equation in case of a damper. Now we can note one very important point here. In case of a rigid body, the torque is proportional to the angular acceleration. Whereas in case of spring, the torque is directly proportional to the angular displacement. And in case of friction, the torque is directly proportional to the angular velocity. So this is an important point to remember. So in this way, till now in this lecture, we have discussed the introduction of mechanical systems, the types of mechanical systems, and the parameters and components of different types of mechanical systems. We will now compare the parameters and components of translational mechanical systems to that of rotational mechanical systems. Now moving on to the comparison between the translational motion and the rotational motion, we can say that mass in case of translational motion is analogous to the moment of inertia J in case of rotational motion. Moving on, force in case of translational motion is analogous to the torque in case of rotational motion. Moreover, spring constant in case of translational motion is the torsional spring constant in case of rotational motion. Similarly, frictional constant in case of translational motion is the torsional frictional constant in case of rotational motion. The displacement in case of translational motion is the angular displacement in case of rotational motion. Similarly, the velocity in case of translational motion is the angular velocity in case of rotational motion. And in the same way, the acceleration in case of translational motion is the angular acceleration in case of rotational motion. Now I want you all to go through the previous slides one more time and compare these terms of translational motion with these terms of rotational motion. I hope you're done. So in this lecture, we have just discussed the introduction of mechanical systems. In the upcoming lectures, we'll be discussing some more concepts based on modeling of mechanical systems. As of now, we are done with this lecture. Thank you for watching this lecture. I'll end this one here. See you in the next lecture.